welcome to the third lecture of this week. In this lecture I will talk about fundamental theorem of linear algebra. So if you remember your mathematics classes, there are many fundamental theorems in mathematics. The most famous can be, for example, the fundamental theorem of calculus, which says that integral is the inverse of the differentiation and differentiation is the inverse of the integral. Or fundamental theorem of algebra, which says that every nth order non-constant polynomial has n roots. And fundamental theorem of linear algebra is also one of the important theorems. At the end of the last lecture I have talked about it a little bit, but now I'm going to write the statement of the theorem and I will prove it. So the fundamental theorem of linear algebra tells us that null space of A orthogonal complement is equal to range space of A Hermitian. Okay? So now we would like to actually prove this. So last time we have seen some examples of this theorem in which this equation was valid. Now let us try to prove it. So I have the proof. In general, with this statement in this form, it is really very difficult to prove this, but by taking the orthogonal complement of both sides, we get an easier but equivalent statement. If I take the orthogonal complement of both sides, null space of orthogonal complement and orthogonal complement would give me null space of A is equal to range space of A Hermitian orthogonal complement. Okay? I have taken the orthogonal complement of both sides, which gave me an equivalent statement, but which is much easier to prove. So before I start with the proof, I'm going to give you some facts. So suppose that I have the following norm, L2 inner product, not norm. So L2 inner product is Y Hermitian X. If you are using the complex conjugate transpose as the star, then this is Y star X. Okay? But I will use Hermitian because that is what I'm used to. So suppose that in one of the elements of this inner product I have an A multiplication. Suppose that I have AX and the inner product with Y. In that case, I have the what does the inner product say? Take the Hermitian of the second element and put it first and then multiply it with the first element. Okay? So I will do the same here. This is Y Hermitian AX. Now I'm going to actually write this same expression in the following form. This is A Hermitian Y Hermitian. Okay? I have just taken parentheses here and I have taken the Hermitian of it. This is the same as Y Hermitian A because Hermitian operator changed the orders of the elements here because of the transpose. So I would have Y Hermitian, A Hermitian is A. Okay? So then I have X. But then this means that I can write this form again as an inner product. So I can write this as X and A Hermitian Y. Of course, these inner products are belonging to different spaces. So this one, so here, this inner product is the inner product of Cn. But this inner product, the one at the end, I find is an inner product of Cn. But they both have the same expression. Why is that? Because Y is inside Cm and Ax is going to be inside Cm. So a vector in Cm, I take their inner product. And in this case, X is inside Cn. And A Hermitian Y is going to be inside Cn. Okay? So what does this tell us? This tells us that if I have an A multiplication in one of the arguments of the inner product, I can take this A to the other side by taking its Hermitian. Okay? So this is X and I have A Hermitian Y, which is the same equation here, okay, that I have written. So it really doesn't matter if the A multiplication is in the second argument, you can take it to the first argument by taking its Hermitian. Now, after seeing this fact, let us concentrate on the proof. Proof is, I'm going to prove this statement, which is a set equality. In order to be able to prove set equalities in mathematics, we use the subset relationships. So if I can show that null space of A is a subset of range space of A Hermitian, orthogonal complement, and if I can show the reverse subset relationship, range space of A Hermitian orthogonal complement is a subset of null space of A. If I can show that both of these subset relationships hold, then I can be sure that there is equality between these sets. So here, the first subset relationship tells us something like this. In this case, range space of A Hermitian orthogonal complement is the larger subspace, A Hermitian orthogonal complement, and null space of A is the smaller subspace. That is coming from the first statement. For the first statement, I need to prove that we have some picture like this in terms of sets. Okay? And the second one is just the reverse. So I have null space of A, and I have here range space of A Hermitian orthogonal complement. Okay? If I can show that both of these pictures are correct, then there is only a single possibility that these two subsets or subspaces should be equal. Okay? They are subsets of each other, which means they are equal. Okay? So let me try to prove part one. So this is part one. I want to prove this one first, and then this is part two. Okay? Now, in order to be able to prove part one, I'm actually going to take an arbitrary vector inside the null space of A, and then I will show that that same vector is an element of range space of A Hermitian orthogonal complement. Okay? So let us say that X is an arbitrary element in null space of A. Okay? So this is part one. Let X be an element of null space of A be arbitrary. Okay? So that means that A times X is equal to 0. Okay? So now this is A times X is a vector in Cm, and this is the 0 vector. As a result, if I take the inner product of Ax with y, any y in Cm, this is going to be equal to 0, because I'm taking the inner product of 0 vector, which is orthogonal to all vectors, and an arbitrary vector y. This is true for all y in Cm. Okay? Now I'm going to apply this trick that I have showed you. So here I will take this A to the other side. That means that X, A Hermitian y, I took A to the other argument, is equal to 0 for all y in Cm. Okay? But this means that X and any vector in the form A Hermitian y should be orthogonal. Okay? X is orthogonal to A Hermitian y for all y in Cm. But what does really this mean? A Hermitian y is, so this is a matrix vector multiplication, and that means that I'm here taking a linear combination of columns of A Hermitian. Okay? So the vector A Hermitian y, if I change y, I would obtain a vector, an arbitrary vector inside range space of A Hermitian. So X is orthogonal to range space of A Hermitian. Why is that? Because any vector inside range space of A Hermitian can be written as a linear combination of columns of A Hermitian. Okay? And this is what this tells. A Hermitian y is a linear combination of columns of A Hermitian. That means that X should be orthogonal to range space of A Hermitian. But if X is orthogonal to all vectors inside range space of A Hermitian, then we need to have X is an element of orthogonal complement of this subspace. Okay? So that means that, so we started with an arbitrary element in null space of A, and then I have showed that it's also an element of range space of A Hermitian orthogonal complement. Okay? So here I have showed this subset relationship. If any vector in null space of A is an element of range space of A Hermitian orthogonal complement, then I should have this type of picture. All right? So this completes the proof. That means that null space of A is a subset of range space of A Hermitian orthogonal complement. Okay? Let us now go into part 2. In part 2, I will try to do the reverse. I will take an arbitrary element inside range space of A Hermitian, and then I will show that it is also an element of null space of A. Okay? So let X inside range space of A Hermitian orthogonal complement be arbitrary. Okay? Then we know that X is orthogonal to any vector A Hermitian Y for all Y in Cm. Okay? Why is that? Because any vector in range space of A Hermitian can be written in this form. And X is inside the orthogonal complement of range space of A Hermitian. That means that X should be orthogonal to any vector of this form. Okay? For any Y in Cm. And that means that X and A Hermitian Y inner product should be equal to 0 for all Y in Cm. Okay? So now I can apply my trick. I can take this A Hermitian to the other side by taking its Hermitian. A Hermitian is A. So I have AX Y is equal to 0 for all Y in Cm. Okay? So we see that here AX and Y inner product is equal to 0 for all Y's in Cm. Okay? So here AX is in Cm and Y is in Cm, and you see that the inner product should be equal to 0 for all Y's. Since AX is in Cm, this equality should hold when I select my Y to be equal to AX. Okay? AX is also in Cm, all right? Because for the inner product to be defined, these two vectors should be in the same space. Y is in Cm and AX is in Cm, and the equality is correct for any Y in Cm. That means that the equality would still be valid if I choose Y is equal to AX, because this is a vector inside Cm definitely. So I can choose Y equals to Cx, which is going to give me AX inner product is equal to 0. Okay? This is just a specific case of this fact here. All right? And I know that this is nothing but the AX norm square is equal to 0. And that means that AX norm is equal to 0. And if norm of a vector in Cm is equal to 0, then that vector should be equal to 0. AX is equal to 0, which means that X is inside null space of A. Okay? So that shows that if I start with any vector inside range space of A Hermitian orthogonal complement, then that vector is going to be an element of null space of A as well. So then this actually shows that range space of A Hermitian orthogonal complement is a subset of null space of A. And combining these two proofs, we complete the proof. So we have a Latin word that is called QED, which says that the proof is complete. Okay? This is an abbreviation in Latin for proof is complete. Maybe Emruzkan told you about it. So this actually completes our proof. Now we know the fact of the fundamental theorem of linear algebra. So let me write here. This is really important. Fundamental theorem of linear algebra. Okay? So now we have proven this theorem, and now we can use it in action. So what I'm going to do now is to summarize the theory for linear equations that we have seen. Okay? So let us start with Ax equals to b. When you start with an equation, and I'm going to write this in an algorithmic fashion. So when we start with an equation, then we're going to ask the following questions. If b is inside range space of A, then there exists an exact solution. Okay? And this is going to be my x. Okay? And if b is not an element of range space of A, then we know that there doesn't exist an exact solution. But we know that we can actually find an approximate solution by minimizing the error. All right? And how do we find it? We first calculate B1 by projecting B onto range space of A. Project B onto range space of A. Okay? And then we solve for the solution of the equation Ax set is equal to B1. Okay? Now the right hand side is in range space of A definitely, because it's the projection onto range space of A. And now we can find at least one X set. And remember, X set is called the minimum error solution. Minimum error solution. Sometimes it is also called least square solution. Least square solution. Maybe least square solution is used more commonly. So not sometimes. Least square solution is used more commonly. And why do we call it the least square solution? Because in order to be able to obtain that solution, we are actually solving implicitly an optimization problem. We know that X hat is nothing but the argument of the minimization with respect to x, Ax minus b. Here I can put a square, and here I'm minimizing the square of a function, which means the solution is the least square solution. All right? So now I will go into the uniqueness. If null space of A is only composed of the zero vector, in that case X set is unique. Then X set is unique. It is the unique minimum error solution or unique least square solution. Okay? On the other hand, if null space of A is not equal to the zero vector, then X set is not unique. Okay? In that case, we are going to be looking for a unique solution by minimizing the norm of any such solution. Okay? So then what we do is that we take an arbitrary solution X set and we project it onto null space of A orthogonal complement. Okay? Take an arbitrary solution and then project it on the null space of A orthogonal complement. But fundamental theorem of linear algebra tells us the following. This null space of A orthogonal complement is nothing but the range space of A Hermitian. Okay? So I have the same x1 given as projection onto range space of A Hermitian of X set. Okay? So these are the same thing. And range space of A Hermitian is the space of the rows of A. And that means that this minimum norm solution is always a linear combination of the rows of A. So remember, x1 hat is called minimum norm solution. Because at the same time it is the minimum error solution, then it is the unique minimum norm, minimum error solution. So let me write it as well. Minimum norm, minimum error, or least square solution. minimum error solution. Okay? And what is the property of this x1? x1 hat is the solution of the following optimization problem. Argument of minimization over all solutions except satisfying this equation, the norm of xset. Okay? It is the minimum norm solution among all solutions satisfying this equation, satisfying the minimum error, satisfying the condition of the minimum error solution. All right? So this was a summary of what we have done so far in AX equals to B. In the next lecture, we are going to see actually some specific cases. We're going to see, for example, what happens when A is full column rank, which means when all columns of A are linearly independent. In that case, we will be able to see that there are specific formulas for this minimum error solution or for the minimum norm solution, etc. But I would like to finalize this lecture with the following interesting arguments. So we know that A is a linear transformation from the domain Cn into Cm. Okay, A is defined here, and I have the null space of A here, and the range space of A is a subspace here in the codomain. Okay. So now let me look at some dimensions. All right. So I know that by the rank nullity theorem, dimension of null space of A plus dimension of range space of A is equal to the number of columns of the matrix. So A is an m by n matrix, okay, times x is equal to B. B is in Cm, this is in Cn, and A is in C m by n. A has m rows and n columns, all right? And here, the rank nullity theorem, according to the rank nullity theorem, this sum is the dimension of the domain, which is n. Okay? So suppose that the rank of the matrix, this is rank and this is nullity. Okay? So suppose that the rank of the matrix is k. Obviously, k is a number smaller than or equal to, is an integer smaller than or equal to n. Okay? Then dimension of null space of A happens to be n minus k. The nullity would be n minus k if the rank of the matrix is k. What is the rank of the matrix? What is the dimension of range space of A? This is the number of linearly independent columns of A. Okay? Range space is the column space of the matrix, and if the dimension of the range space of A is k, that means that that matrix has k linearly independent columns. Okay? Now so I know that when I know rank, I know the number of linearly independent columns of the matrix. What about the number of linearly independent rows of a matrix? Do you think I can say anything with these results here so far? The interesting thing is actually the answer is yes. So remember, I can actually write Cn as the direct sum decomposition, orthogonal direct sum decomposition of null space of A and null space of A orthogonal complement. Okay? I can do this for any subspace of Cn. All right? And I know that by the fundamental theorem of linear algebra, I know that this is nothing but range space of A Hermitian. Cn is equal to null space of A and range space of A Hermitian. Okay? This pass from here to here is done by the fundamental theorem of linear algebra. Okay? And what does this tell us about the dimensions? If I have a direct sum here, the summation of the dimension of this one and summation of the dimension of this one should be equal to m. Okay? Let us write that. Dimension of null space of A plus dimension of range space of A Hermitian is equal to the dimension of Cn, which is n. Okay? I know that the dimension of null space of A is n minus k. What about the dimension of range space of A Hermitian is then? So just subtract n minus k from n, and you will see that this is the dimension. This has the dimension k. All right? So then, what is this dimension? Dimension of range space of A Hermitian. Range space is the column space, and the column space of the Hermitian of the matrix is nothing but the rows of the row space of the matrix. Okay? In A, I have rows, and when I take A Hermitian, those rows would become columns. Range space is the column space. So a column space of A Hermitian is nothing but the row space of the original matrix. So here I can say that dimension of range space of A Hermitian is the number of this dimension is nothing but the number of linearly independent rows of A. Okay? Because this is my row space. Range space of A Hermitian is our row space. It's the column space of A Hermitian, but A Hermitian's columns are the rows of A. That is why range space of A Hermitian is the rows of A. Okay? Is the space of rows of A. So what does that mean? So you see that I started with the assumption that dimension of range space of A, the number of columns of linearly independent columns of A is equal to K, and I ended up with the following result. Dimension of range space of A Hermitian is the same. It is equal to K as well. So the number of linearly independent rows of A is again equal to K. So this is equal to K, and this is equal to K. From this we get the following result. Well, dimension of range space of A is equal to dimension of range space of A Hermitian. What does this tell us? Number of linearly independent columns of A is equal to number of linearly independent rows of A. It is really a magical result. If a matrix has k linearly independent columns, it should at the same time have k linearly independent rows. Okay? So fill in an arbitrary matrix with some random numbers. If the number of linearly independent columns is k, the number of linearly independent rows will be at the same time equal to k. So here, just 1, 1, 2, 2, 3, 3. How many linearly independent columns? There is only one linearly independent column. I can choose this one, this one, this one, or the others are always linearly dependent. So there is only one linearly independent column, and when I look at it, its rows, then I would have only one linearly independent row. And similarly, if I just change a number here, 1, 2, 4, then you see that I have two linearly independent columns. And as soon as I start to have two linearly independent rows of the matrix, okay? So this is really a magical result. The column rank of the matrix is equal to the row rank of the matrix. Sometimes we call this like this. So the column rank of A, which is the number of linearly independent columns of A, is equal to row rank of A. which is the linearly independent rows of A. Okay, so both of them are equal, and therefore sometimes we really do not differentiate between these things. We just say this to be the rank of A. Okay, so the rank of a matrix is the number of linearly independent columns or the number of linearly independent rows which always have to be equal. Okay? So that completes this relatively short lecture. So in the next lecture we are going to see some specific cases. What happens when we have a full column rank, which means that all columns are linearly independent, and what happens when we have a full row rank, if all of the rows of A are linearly independent, and what happens if A has both full column and full row rank. And in that case we will see some specific results of AX equals to B using some and deriving some analytical formula for our solutions, for minimum error and for minimum norm solutions. But that's going to be all for this lecture. Thank you for watching. Bye-bye.